So today, what I want to go over is nuclear chemistry and what happens in a nuclear reaction. Also, why some isotopes are stable, ones are not, and what types of radiation we see being emitted. So, first of all, before I go over this, I want to go over the difference between stable and unstable isotopes. So, some people, when they hear the word isotopes, they assume that the material that we're talking about is dangerous, but this is not always the case. So, I want to go over what the difference is between the two. So, first of all, when we look at our atom, the neutrons in our atom are present to kind of hold the nucleus of our atom together. So the reason for this is when we think about the protons are in the nucleus, they all have the same charge and they repel each other since they have like charges. So neutrons are there to kind of buffer those protons so they're not repelling each other as much. So neutrons kind of act as a glue to hold the nucleus together. So when we look at isotopes that are stable and compare those to unstable isotopes, the difference that we see is stable isotopes will stay the same over time. So if we have some carbon-12 come back billions of years from now, the amount of carbon-12 will be the same. However, if we look at unstable isotopes, these are radioactive. They will emit radiation and they will decay over time. So if we have some carbon-14, for example, come back billions of years from now, the amount of carbon-14 that we have will be lower. It will decrease. Now, what happens when we have radioactive decay is there's three main types of radiation that we see. The first type are alpha particles. These are helium nuclei. These have two protons and two neutrons. Because they have some mass and they have some charge, it's pretty easy to protect yourself from alpha particles. So if you just have a piece of paper, that will block some alpha particles. So they're not very dangerous. Beta particles, though, are more like electrons. So they have very little mass, but they also have a charge. So it's a little bit more difficult to block beta particles because they have such a small amount of mass. So you need to use a piece of aluminum foil, for example, to block some beta particles. The most dangerous type of radiation are gamma particles. These are kind of like light. Basically, they are light. They have no mass. They do not have a charge. They're very similar to X-rays. So they're the most dangerous, and we need to use a piece of concrete to block it, or maybe a piece of lead. Kind of like when you go to the dentist and you get your X-rays, you wear a lead apron to protect other parts of your body from the X-rays. We would do a similar thing with gamma particles. So we go from the least to the most penetrating on this slide. Now, when you have a nuclear reaction, what you are doing is you're changing the nucleus to make it more stable. So it's trying to, I'm just going to ink that on here, trying to become more stable. So you're changing the nucleus. A chemical reaction, we're just rearranging the atoms. The nucleus is not going to be changing. Chemists worry more about chemical reaction. A physicist would worry more about nuclear reactions. So when we look at the slide, if we have a chemical reaction, we're just rearranging the atoms. Here we have water being formed. When we have a nuclear reaction, we're actually changing the nucleus, and we have a lot of energy being given off. So on the left-hand side, this is an example of fission. We have a neutron hitting a uranium-235 atom and splitting up into two smaller nuclei. So when we look at elements on our periodic table, some elements are very unstable. They're going to be naturally radioactive. They will spontaneously decay to emit either alpha particles, beta particles, or gamma particles. Transuranium elements at the very bottom of our periodic table, these have atomic numbers greater than 92, and these are naturally radioactive, and none of these are going to be found in nature as a result. So when we look at atoms or nuclei, the way to predict if they're going to be stable or not is really looking at the ratio of protons and neutrons. So this larger nuclei are going to be more unstable. So I'll just ink that on here. Large nuclei are more unstable. So if we look at atoms with atomic numbers greater than 83, these are all unstable, and some of these are found in nature. Atoms are trying to decay to form more stable, non-radioactive atoms. That's their goal. That's why radioactive decay occurs. So some elements or some nuclei, they can just be decay in one step to form a stable nucleus. Some of them, but most of them need to decay over several steps to become stable. So usually what we see is when we have a radioactive decay occurs, the product will also undergo radioactive decay to eventually reach stability. So it's not one simple step usually. So we can predict if a nucleus will be stable or not by looking at the ratio of neutrons to protons. What we see is that if the ratio is greater than or equal to 1, or and less than or equal to 1.5, the isotope is stable. So there's a band there where is stable. If it's less than 1 or greater than 1.5, it's unstable. So if you look at the bottom of your periodic table, and if you were to calculate the ratio of neutrons to protons, you would find that most of those have a ratio where it's less than 1 or greater than 1.5, and those are all going to be unstable. Now, when we look at uranium-238, this is just an example, like I was saying, that a lot of elements, they have to go through several steps before they eventually become stable. So uranium goes through many, many steps, giving off alpha and beta particles until eventually it becomes lead, which is very stable. One of the products along the way is radon. So a lot of you guys probably have radon or have had done radon testing in your homes. Some of you guys might have radon pumps in your basement. And what we see is that in New Jersey, a lot of minerals in New Jersey contain uranium-238 in very small levels. And this eventually does decay to form radon-222. We look on it, this is about midway through the decay process for uranium-238. And radon-222 does actually cause cancer. It's a gas, and it can collect in your basements. And if you have new construction and very good insulation, it's easy for this to get trapped in your house and to collect at lower levels of your house. So it's important to test for. So this is just something that is naturally occurring because of natural radioactive decay that occurs in our region of the country. So now I want to go over how we symbolize nuclear reactions, how we write nuclear reactions, also why certain types of radiation are emitted. For example, why sometimes alpha radiation is emitted, why sometimes maybe beta radiation be emitted. So first of all, when we have a nuclear reaction, we're going to be using the isotope symbols that we used previously. So remember, the atomic number is Z. That's the number of protons in the nucleus. That's going to be on the bottom of our atomic symbol. Mass number is going to be A. That's the number of protons and neutrons, and that will be on the upper left-hand corner above by our element symbol. So we're going to be seeing these symbols just like before. The different types of radiation we've been talking about are here. So we have gamma, alpha, and beta. And we have some new ones. We have neutrons, protons. We also have something called positrons. So why don't you write these down? These, if you notice here, protons can be either symbolized as a P with a 1 and a 1, or an H for hydrogen and a 1 and a 1. Alpha particle you can see symbolized either as a helium nucleus or as an alpha symbol. We have electrons, which are beta minuses, sometimes referred to as beta minuses. We have positrons. These are sometimes referred to as beta pluses. So either beta plus or positron. So these are just different symbols you're going to see in nuclear reactions. And we're going to go over, like I said, why sometimes an atom or nucleus might emit alpha particles, why sometimes it will emit electrons or positrons, and so on. So if you just pause this for a minute, you could write down these particles. Okay, so I want to first go over the different types of beta decay, beta minus and beta plus. So beta minus, and this is basically an electron, will occur when a nucleus has too many neutrons. So remember the band of stability, the neutron to proton ratio. And sometimes if there's too many neutrons, the ratio is going to be greater than 1.5, we might have beta decay. So I'd like to think of this as a neutron kind of emitting an electron and then forming a proton. So neutrons kind of breaking apart, you could think of it, into a proton and an electron. It's not exactly like that, but that's how you can kind of think about it. So beta minuses are just basically like normal electrons. Another type of radiation is beta plus. We call this, again, positron emission. And this might be a situation where we have a nucleus with too many protons. So I kind of think about it as a proton kind of splitting up into a neutron, and a beta plus particle. So here we have more neutrons being produced. So this reaction down here is just an example of a situation where you have beta plus or positron emission. Another type of radiation that we see is electron capture. So here we have a situation where we have a nucleus with too many protons relative to neutrons. So we have a proton combining with an electron to form a neutron. So this will reduce the number of protons and increase the number of neutrons. So about that. The next one is alpha decay. So we also have situations where the nucleus is too large. So here we have a nucleus with way too many protons, way too many neutrons, and it emits alpha particles. This will also reduce the size of the nucleus. So we have an example here with uranium. Uranium is a very large atom. It often does undergo alpha decay. So here we have uranium 238 emitting alpha particles and is forming thorium. So that's just another example. Okay, so in all these types of reactions, we can write a nuclear reaction. So when we have a nuclear equation, the first thing we want to do is to balance the mass number in our equations. So here we have a fission reaction. We have uranium-235 that's being hit by a neutron, splitting apart, it's fissioning into cesium and rubidium. If we look at the upper number in each of our symbols, that's our mass number. We notice that on both sides of the equation, the mass number is going to be the same. So we notice here that we distribute the coefficient of 2 to both a 1 and the 0. In a reaction, we also want to make sure we conserve the atomic number or the nuclear charge. We look at the same reaction, and we look at the atomic number at the bottom of each symbol, and we see that 92 plus 0 is going to equal to 55 plus 37 plus 2 times 0, which is 0. So the mass number and atomic number is going to stay the same. Okay, so let's go to the next slide. So look at this reaction here. We have polonium-212. It's decaying by alpha emission. So when you see emission, that means the alpha particles are product. See here we have polonium-212. It's producing alpha particles. So you can think about what plus 4 would give you 212. That should be 208. And then what plus 2 would give you 84? That should be 82. And if we look at our periodic table, we would find that this element with atomic number of 82 would be lead. So the missing component is going to be lead 208. So that would be how we would figure out the missing thing in our reaction. Okay, so we're going to go through a couple more problems like this, and you're going to be working on a sheet with balancing nuclear equations.